Testing, testing. Are we here? Yes. Good morning. Good morning, everyone. How are we doing today? Woohoo! Oh, wait. This is hot. Hot. Okay. Oh, I need to set up my. I need to set up. Excuse me. I need to set up my drawing board, my whiteboard. So I need to. Where is this? I have a lot of stuff here. I need to set up my alternative computer. How's everyone doing? Ali, Nylan, good morning. How are you doing, folks? Okay, what do we got going on here? Am I going to be drawing? Yes, I'm probably going to be sketching stuff this morning. I'm a little white, am I not? I'm a little. What is my? And what is this? Oh, okay. My face looks a little burnt, right? Oh, there's a lot of light. Okay, and now I need to, well, I am not connected to anything right now. So I am just going to put this in here, put this in here, while my computer is hot in Milan. It's very cold here in Boston. It's been raining for 3 days nonstop. It's kind of not nice. I wish it wasn't. I wish I was in Italy though. I had a really nice time. I spent a month in Italy 3 summers ago. I was doing marble sculptures with robots. It was so nice, like so ridiculously nice. Anyways, I'm going to connect to my, yes, there you go. And then I'm going to set up my sketchbook here. So now I have my sketchbook right there. Exactly. There you go. Okay. I was in Garfagnana, Ali. I was, you know Carrara? So the mountains behind, they had a bunch of marble quarries, and they had a town that had robots and to do marble and stuff. So I did a 1 month artist residency in this thing called the Digital Stone Project, which is a nonprofit in the US that organizes workshops for artists and sculptors. And they do like a summer workshop every summer in Italy, back before COVID, right? Where you go there, you spend a month carving marble, you play with robots, it's great. So, and then I also of course, every weekend I would just go down to Pisa, to Pietrasanta, to La Spezia, Cinque Terre, all that area. It was really nice. I had a really nice time, I have to say. I mean, who wouldn't? Doing marble sculptures with robots. That's like the most fun thing you can do on Earth, probably. If you're a little nerdy like me. Okay. So, what do we got going on today? Oh, God. Excuse me. Oh, God. Okay, so what do I have to do? Actually, that was great. Ah, that was great. So, sorry, folks. I'm looking through my notes here about what do I have to do for today. And what is my plan? for today? Um, what is my plan for today? So, oh yeah, so my, I need to do this. Mhm. Yes, if you Google, Ali, if you Google Digital Stone Project, you can find all the information you want about that. And also, if you Google my name and Digital Stone Project, you should find a video, a documentary that I did about the work that I did that month. So you can probably post a link somewhere on the Discord channel or here or somewhere. I don't know. Mm-hmm. Okay. All right. So what are we doing today? Well, let me start. Let me start by the beginning, which is yes, 3, 2, 1, 2, 2, 2. Hello, hello. Good morning. This is Jose Luis, and this is Parametric Camp. We do computational design live streams. You can follow us on social media to get to know when we go live and when we publish videos. We typically do live streams on Fridays, but for the past 2 weeks, we've been working on this one series that I'm trying to wrap up called Introduction to Parametric Modeling, which hopefully we're going to wrap it in the next 3 days because I'm leaving. I'm taking some time off starting Thursday, so we need to just wrap it up today, tomorrow, and on Wednesday. So we're going to be live streaming twice for the next 3 days, and hopefully wrap it up. Oh yes, we have a Discord channel. In case you want, we have a Discord server. In case you want to join the conversation throughout the week, I also announce when we go live there. I also announce when we go live on a Google Calendar that you can subscribe to. I'm posting links on the chat, but also those links are here on the description of this channel. So what are we doing today? In the previous videos, we have done randomness. We have done intersections. So we've done basic all the geometry types. We've done data manipulation, data trees, data lists, a lot of exercises on how to manipulate that. You can post it on, I don't know, Ali, you can post it on work sharing channel, or you can post it on the bonfire channel, whatever. Then on the live channel, maybe you can post it on the live channel because it's a conversation that we're having live right now. So maybe you can do that. I don't know. That doesn't really, maybe in work sharing because it's part of my work, if you will. So I was saying and then the last we've done is we've taken a look at intersections. We've done an exercise on that. We've taken a look at randomness and how to generate random numbers and why that's important. And we are in the middle of doing some exercises, doing a few exercises on randomness. And I have written here 3 exercises that I want to do. I want to do an exercise where we model a surface and we populate it with grass threads, and we make a small exercise where we move them with the wind, for example. Oh, Ali, I see you're posting it. Thank you for that. Oh, but that's not the one. That's not the video that I mean. This is just that video is only a time lapse, but I have a full documentary. Like a 15-minute documentary where I explain the project, what we did, etc., etc. Let me look it up. It's called the Digital Touch, I think. Exactly that one. I see it right now. Okay. So I was saying, I want to do an exercise where we're going to model some grass threads blown by the wind. I want to model a facade. I want to say we have a facade, and I want to populate this facade with stripes of random panels. That's another thing I want to do. And then I want to do this one. This one is going to be mad cool. This one is going to be, we're going to model a brick wall, and then we're going to make it explode parametrically. How cool is that going to be? That's going to be really cool, actually. So why don't we just get started? So I'm going to, oh, sorry, I'm going to open Rhino here. I'm going to open here. And then if anyone has an idea of exercises that we could do to discuss randomness, that would be great, actually. Yeah. So you're welcome to put ideas on the chat. Now I want to take a look real quick at a couple of maybe examples. See if I have examples of that somewhere. Patterning. Oh no. No. Okay. I think this is not going to be here. What am I looking for? Okay. All right. So, and thank you, Terence. Yeah, I mean, to me, I'm not even aware that this is Memorial Day or not. Shatter array of curves in the domain of length, blah, 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 they be shattered randomly using jitter. Oh, but what would be an application for that, Ali? How could we turn that into an application? Okay, so where's here? So let me start. So we're going to do random grass. So we're going to do random grass. So what we're going to do is, what are we going to do? What are we going to do? How are we going to how are we going to do this? So we will record the introduction at the end. So what I want to do first is I want to create the grass, and for the grass I want to create the grass and then after we create the grass, we are going to sweep it with wind. we're going to affect it by some kind of wind. Mm-hmm. Mm-hmm. I think that's what we're going to do. Okay, so in order to do that, I'm going to start off from some kind of landscape topography like this, some kind of topography like that. And then what I want to get is I want to get grass that kind of looks like this. And you can see that basically, actually I don't like this very much. So I'm going to So what I want to do is I want to use to discuss that the grass will have like some kind of perpendicular route to the surface, but it will also end up being vertical, and it will also have this separation of this separation. It will also have this like random height somehow here. So that's one thing. Also, another thing that I would like to do, and then I would like to explain how. The first thing that we're going to do is we're going to get random points on top of the surface. And then from those random points, we're going to calculate the tangency. RGB. We're going to calculate the tangency to the surface. And then we will use that tangency to find an intermediate point that maybe is somewhere here, somewhere here, somewhere here, somewhere here, here. That defines the tangency of the root. And then after that, we might just as well do some kind of vertical C where we take that and we do like random heights. And we use that to create another family of points, which are going to be somewhere here. So that's going to be the first step. And then we will figure out after that how to make the wind sweep the grass in a way. We're going to figure out how to make the wind sweep the grass. Yes. Okay, so let me just get started then. As usual, this exercise, I would like to start by taking a look at sketching. Blah, 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 blah. Let's start over again. Do I have anything? Do I have a meeting or anything going on today? No. Good. So that's okay. As usual, we're going to start in the whiteboard and we're going to take a look at the steps that I think we're going to follow in order to make this parametric model happen. And I think in general, we're going to follow two very different stages. The first one is going to be modeling the grass patch. And then at a second level, The second stage will be taking what we have and then making sure that it oscillates as if the wind was sweeping over it. So we will first model it in a static way, so just the grass, and then the second phase will be the grass modified by the wind. So for the first stage, we're going to follow a fairly simple process, which is going to be, we're going to first find, where is my mouse? Let me first find my mouse, right? So we're going to first find we're going to model a set of grass threads that are going to be popping out or growing out of a non-planar surface. We're going to imagine that we have some ground and then that the grass is growing out from it. And if we want to follow that logic, then what I would like to propose is a method that looks something like this, where the grass will kind of always like grow out perpendicularly from the surface. If we have an uneven patch, I think vegetation typically starts growing out perpendicular to the slope where it's growing. I'm not sure that is actually botanically true, but I mean, for the sake of modeling, we're just going to assume that that's the case here. However, as the grass keeps growing, it's not going to keep growing in the direction of the surface. It's going to keep growing in the direction of opposite to gravity. So that's why I would like to model the grass in a way that looks like it's growing out of the surface, but then it's growing up towards the sky, if you will. In order to do that, and because we want to make it look a bit more natural, what I would like to do first is I would like to find a collection of random points on top of that surface. And as we already know, you already know me, those will probably not be points, it will probably be planes, because I would like to also know additional information from the surface, which is the orientation. So from those planes, I will probably take the perpendicular vectors and use those vectors to move the base points a particular amount along that direction, so that we use that second point as one of the points of the curve that we're going to use for the grass. And then that way we will have the intermediate point be kind of perpendicular to the surface. And then at a third stage, I would like to take all those points and calculate a vertical C vector. That is not going to be the same for all of them. It's going to include a little bit of randomness because not all grass grows at the same rate, okay? And use that vector to create the third point that I will need to create a curve between those 3 points. And those curves will be the grass threads. Now, how are we going to move this with the wind? We will come back to that. That will be the advanced version of this exercise. But I think this part should be pretty straightforward. So let's go back to Grasshopper and see how can we implement this. Okay, so let's go back. So where am I? Okay, so let me bring in this surface here, for example. Yep. For example, and I'm going to move this a little out of the way, and I'm going to shade this a little bit. Nope. Ghosted. Okay. And then what am I going to do? I'm going to place some bifocals to start with, and then I'm going to bring in the surface. And then what other parameters do I think I would want? Are you there? Hello? Yeah, my computer is doing weird stuff. Sorry about that. And then this panel should go here. Okay. And then, so here I'm going to say, how many threads do I want? It's going to be like 1,000. And then then I'm going to add here some kind of slider, like root tangency. and the distance, and I'm going to copy paste this and say grass base height. And then I'm going to add another one, which is going to be grass random variation. So I'm going to set this at 1. Root tangents is going to be, for example, 3. And then base height is going to be 10, for example. I don't know. And this is going to be 100. And I think I'm going to I'm going to leave it like that. And then I'm going to save this what is exercise are we doing here? E22. Wind swept grass. And this I'm going to also save somewhere. Wind swept grass. Okay. So, are we ready for this? I think I am. Probably. And then from the previous exercise, I'm actually going to take stream. I'm actually going to take already the example where we populated. Yes, I'm going to add a seed there. I'm going to add a seed here. I'm going to add a seed. Random seed. Okay. I'm going to crank this up to 1,000, for example. It's going to be the seed. It's going to be the seed. Construct point, and then domain 0 to 1, blah, 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 and the surface is going to be there. And I'm going to get all these planes. Fine, and now if I set one surface and I plug this in here, I get all these planes. Point, normal, U, V, the frame. Here. Wait, what? Interesting, this is wrong. Ha ha ha. Okay, so this is actually not, this could go here actually. Huh, okay. What is it? How many numbers? Oh, I see. Okay, so I'm going to disconnect this and I'm going to clear the values. I'm going to disconnect this because I want to talk about this as I connect things up. All right. All right. How's everyone doing? Divas, howdy, what's up? How are we doing today? Okay. So let's get started. And All right, so let's start with the basics. I have created some random design surface, like a topographical surface, if you will, from in Rhino, and I'm going to bring that surface into Grasshopper by dropping in an empty surface parameter component, right-clicking, setting one surface, and then selecting this one. I have also added a bunch of sliders, for example, for how many grass threads do we want, what is going to be the random seed. We have seen this in previous videos, and then some parameters for the geometry of the grass thread. So for example, how far away from the surface is going to be that point that we're going to define as the tangency, what is going to be more or less the total height of the grass thread, and how much variation is going to have randomly. So how far off are going to be some of the threads from each other. Now, what the first thing that I would like to do as per our sketch is to find the collection of planes that is randomly distributed on top of the surface. And if you remember right from my previous video on this series where I was doing a landscape with random vegetation, what we can do is, in order to find random planes along that surface, is to create a set of random points from zero. It's like to find a set of random points on the surface. And in order to do that, what I can do is I can generate a series of random values from 0 to 1. So I can use the random component to generate numbers from 0 to 1. How many of those random numbers are going to be? We're going to generate as many as we have grass threads. And if you remember, with the seed of the random engine was going to be this one number that we determine to make sure that it's always, to make sure that the seed is controlled. And then if I do that, you can see that what I generate is a list of numbers from 0 to 1. How many? Well, 126, which is what I had here in count. And so those can be the U values of the planes on this surface. And if you remember, we also discussed how we wanted to create another list of random values from 0 to 1 for the V directions. But in this case, and the domain was also going to be 0 to 1, the amount was going to be the same. But in this case, the seed needed to be different from the previous one, because otherwise we would get the exact same list of numbers, and therefore all the points would be aligned on a diagonal. So that's why what we do is we take the seed, we add the value of 1, for example, so that we have another different seed, and then that way we have a different list of numbers. So if you can see here, now we have a different list of numbers from the beginning. If we had plugged in the same one, we would have gotten the same list of numbers. We use that to generate a collection of points which we will use as UV coordinates on the surface that we want to evaluate. So if we plug in the surface here now, and we make sure that this surface has been reparameterized so that the domain in each one of the directions is guaranteed to go from 0 to 1, then we can turn this on and we can see how we are getting a collection of frames, a collection of planes that are distributed in a random way on top of the surface. These planes will now be the base for all the calculations that we're going to be about how the grass grows away from the surface. The next thing we need to do now is we need to calculate the second family of points. Those are going to be the points that are going to define the tangency of the root of the grass. So that's basically going to be taking all the points that we have on top of the surface, so the center of those planes, and moving them in a normal direction, a controlled amount. How much? Well, it's going to be however much we have defined with one of our parameters. So here, for example, the tangency of the root. So what I can do is I can say I have all these points, right? that are here when I deconstructed the planes. And I also have the C vectors for each one of the planes. So what I can do is I can multiply each one of the C vectors of the planes by the root tangency. And then just for the sake of visualization, I'm going to place here a display component for vectors. And I'm going to visualize these vectors anchored on the center of the planes. You can see that these vectors are going to be the ones that are going to define the tangency. And if I want more or less tangency, the only thing I have to do is I need to just change the slider. And then with this, then creating the second family of points is going to be as easy as moving all the centers of the planes by these multiplied vectors so that we obtain points that are away from the original surface. How much away? Well, right now, if I do 0, then they're going to be exactly on the surface, and if I do more, they're going to be more farther away. Okay? All right, piece of cake. And then the last thing is that now what we need to do is we need to figure out this family of points. This family of points is going to be perhaps a little bit more involved, but it's also going to be super easy because what we're going to do is we're going to take all the points that we just calculated, the ones on the root tangency, and we're going to move them in the z direction a controlled amount. How much? So much that in a way, the total length more or less equals this parameter that we have defined, which is going to be the base height. So if the tangency is at more or less 3 units, then we need to move these points 7 units farther up in the z direction in the z direction, so that the grass more or less overall has a tan. We don't really need to be very precise here. So I'm going to subtract from 10, I'm going to subtract the value of 3. That gives me a 7. And then I can multiply that 7. I can multiply it by a c vector so that I get a c vector that is 7 units positive. And then I can just take all these points and then I can move them in the c direction, a controlled amount. If I now generate an interpolated curve, for example, if I generate an interpolated curve between the first points, the ones that are on the surface, the second points, the ones that are on the define the tangency, and the third points, the ones that define the top, then I get this nest of points, which kind of looks cool, but is not exactly what I wanted. And what have we said already? Whenever we have problems and whenever Grasshopper is not doing what we think it should do, what is the likely culprit? Who is probably guilty for this? We have probably some data problems. The data problem is going to be that if you look at the structure of the data, here what we have coming out is a one single list with 126 elements, whatever. Then if we look at the second input, we have the same structure, and if we look at the third input, we have the exact same structure. If we mimic what's happening in this input by plugging in this panel, the first one, and then adding with the shift the second one, and adding with the shift the third one, you can see that what we end up with is with a list of 3 times 126, which means that this component is trying to create one curve throughout the 300 plus vertices. And that's not what we want. What we want is one curve per 3 elements. So what we need to do is we need to graft this tree so that the structure looks something like that. We have one branch per element, and then we need to graft we need to graft all the other ones. So this one here, we also need to graft the third one here. And now when each one has that structure, you can see that when I merge them together, now I'm going to add with the shift here, and I'm going to add with the shift here. You can see that because they have the same branch names, when I graph them and add them together, each element is combined under the branch that has the same name, and therefore I have created lists, different lists that contain the base point, the the tangent point, and the top, the tip point. And as I do, if I plug this into here, now you can see that I have created all these grass threads. Sorry, I have created all these grass threads that are kind of, you can see they are growing perpendicularly out of the surface, but they end up getting straightened up to the vertical. And actually, I don't think, if you ask me, I think this curvature here doesn't look very natural to me, because I don't think grass goes back this way, and I think the problem is that we're using interpolated curves. So if we were to use control points instead, so let me try doing control points, just creating a NURBS curve, like a simple NURBS curve. I think it will give me a result that looks a bit more natural. So yes, this looks a little more natural to me. If we look at this, you can see that all the tips are now much more vertical. There's no weird curvature, but we still get the effect of growing, of kind of growing outside from the surface. And if I play with the tangency, you can see that little tangency, you see now all the threads are vertical. More tangency, you can see how the curves are now adapting even more to the surface, but they all end up very vertical, which I kind of like. So I'm going to keep, perhaps, I guess, like a larger, I'm going to keep something along these lines here. Okay. Now, what it doesn't look very natural is the fact that all of them almost look like they end up in the same place. They're basically replicating the surface geometry perfectly. It's almost like we have hairdresser come and like chop all the grass at the exact same height. And I don't think that's very normal. So what we want to do is we want to give this grass, we want to give it a slight variation. So what we want to say is, what we want to do is we want to say, let's say we had all the base points here at the same level, right? Because we had hard-coded. What I want to do now is I want to make sure that each one of these has either randomly been increased a little or decreased a little, or increased a little or decreased a little, decreased a little, increased from the baseline. So what I'm going to do is I'm going to calculate a collection of random numbers that go from minus random grass variation. So for example, 2 plus grass variation. So if we say that the grass variation is going to be 1 unit, I want all these points here to go up or down a distance that is between the range of -1 and +1 randomly. So how am I going to do that? Well, it's going to be very easy. I have the random grass variation. So I want to create a list of random numbers. I'm going to go to set, sequences, random. And remember, the random asks me for the domain of the random range. So what I'm going to say is I'm going to create a new domain. I'm going to construct a domain that is going to go from negative, whatever this value is, to whatever this value is positive. So I'm going to do that. And then you can see that if I plug in a panel, I get now one single value. Now I need however many values, 120, whatever. And you can see that I'm now getting values between +1, more or less, and -1, more or less. If I now take these numbers and I add them to the list of the base height, which we computed, it was the total height minus the tangency. If I add those two together, then what I will end up is with a list of random heights that are whatever the base was, 7, for example, I think we said it was, plus or minus random values between -1 and +1. And therefore, if I now use those as the C heights for the vector, you can see that now I have a stronger variation of the grass threads. Can you see that? And I can now play with that value. So if I set that to 0, you can see how now they're all aligned to the geometry of the surface. But if I crank that up, you can see now how I have a lot of variation between, let me, wait, you can see how I have a lot of variation between very short threads and very large threads here, okay? So I'm going to leave this at 1.5, perhaps, maybe 2, I don't know. What do you folks think? Okay, I'm going to leave that at 2, maybe, and that's going to be my. And I think with this, we already have a nice baseline, so I could already bake the curves here. I could group them and I could bake them, and then I could do like a little bit of whatever, and I already have this kind of grass that is protruding or growing out of my surface patch. Okay, which I think is kind of nice. Now that we have the base, now the next thing we're going to do is let's try to see how can we make this grass oscillate a little bit based on some hypothetical wind. It's not going to be very complicated. You're going to see it's going to be okay. Let's take a look at how it goes. All right, can you give me a second? I'll be right back. Hold on. Okay. All right. And then I am going to how am I going to explain this? How am I going to explain this? Well, I can draw a diagram here, right? And I can say the baseline of a grass thread is going to be this one. It's going to be, we have the base, we have the root, and then we have the top. And we have created a nerves curve between them. So now it's not touching as per the diagram. And then what I want to do is I want to instead move the top point I want to move this point in this direction and this direction, in this point in this direction, so that my grass thread oscillates between this state and this state. So for what I would like to do is for each one of the threads, I would like to calculate a distance I would like to cut how. Interesting. Maybe what I can do is I can do it for all of them together and then I can do it individually. And that will be easier to explain. So what I can do is I can say, well, so what I can do is like, if you remember, I can use a sine wave as something that oscillates. The sine of an angle, but it doesn't have to be an angle. It can be just the time, for example. And I'm going to explain that. I think I'm going to explain that with a drawing. So okay. Okay. So what we have right now looks something like this. We have 3 points, the base, the tangency, and the top, the tip, right? And we have a grass thread that goes through them. It's not really through because we decided to use a control points as opposed to interpolated points. So the thread actually doesn't go through the tangent point, but it doesn't really matter. But what I would like to do is to give it an effect that the wind is blowing over it. What I would like to have is some kind of control over where the tip is, and I would like that tip to be oscillating between two states, one that is like farther to one side and one that is farther to another side, for example, so that given a parameter that can be the time, whatever, blah, 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 then the grass is going to be oscillating between a maximum and a minimum. As you have probably imagined, anything that means oscillating between two states, it's typically implemented using some form of the sine or the cosine function, because it turns out that they are really good at given any value, giving you a value between 0 and between -1 and 1 that oscillates. So typically, this would actually be the cosine, technically speaking, because the cosine of 0 is 0. But for example, yes, so the cosine of an angle would be a graph like this, which means that, for example, if instead of thinking about the angle, what I think is about the cosine of time, as time goes by, when time starts at 0, the cosine is 0, so the grass thread would be at the rest position, if you will. Then as time goes by and we approach a time of half pi, then the oscillation would be maximum, which would be +1. And then as we keep going over time, we reach again an oscillation of 0. And then as we keep going, now we reach a value of -1. And then as time keeps going, we go back to 0, etc., etc. So if we take this point and we move it in one direction, a value controlled by the cosine of some number, This is typically an angle, but in this case, we're going to refer to it as time, because as we increase the time, the oscillation goes back up and down. So if we move that point to the left or to the right based on the cosine of time, then we will have this effect that we are looking for. Let's take a look at how to do that for all the points in my definition. So I'm going to remove this thing that I baked. I'm going to go back to ghosted, and I'm going to take this, exactly. And then what I'm going to do is I'm going to define a new parameter that I'm going to call, for example, time. And it's going to be something like this, for example. I'm going to call this time. And then what I'm going to do is that at any given point, I'm going to calculate the cosine of time. All right? And then the cosine of time is going to give me a value. For example, for the value of 0, the cosine is going to be 0. It's going to be 1. So it was actually the sine function. That was a big flop. So I'm going to do the sine function. The sine of 0 is 0, exactly. And then what I'm going to do is, once I have my points, these are the points that I have moved in the x direction. Once I have those, what I would like to do is I would like to move them, for example, in the y direction, an amount controlled by this sign. So I'm going to create a unit y vector. I'm going to plug that in here, and I'm going to now take all these points and move those points, the ones that are the tips, I'm going to move them by an amount that is going to be the sign. And let's check out what's going to happen. As soon as I do increment the time, can you see how the points are moving back and forth as I change my time? And therefore, if I now use those points to generate the curves, what you can see is that all the points of the grass are oscillating back and forth, based on time. All right, how awesome is that? Now, this doesn't look very natural because when wind is, if you imagine wind sweeping through a field of wheat, for example, not the whole wheat doesn't move in the same pace. You can actually see these kind of ripples. You can see these kind of waves that are spreading over the wheat field. So what I would like to do now is I would like to improve this so that all the grass doesn't move at the same direction, but it moves on waves, if you will. Let's take a look at how to do that. Let's take a look at how to do that. Okay, I'm going to start grouping things together here because otherwise it's going to get very crazy very soon. And then oopsie. Okay, now we're going back to to the whiteboard, and in the whiteboard I'm going to clear this up. This is the sine of t. That was pretty much, this is the sine of t. I'm going to save this. And how am I going to say this? What I'm going to do is I'm going to imagine that there is some kind of wind element here, and that the wind is blowing in this direction, right? If I use that direction to I'm going to imagine there is some kind of wind here. Oops, nope. I got it. What have I done? There you go. I'm going to imagine that there is some kind of wind here and that it's blowing in this direction, sort of. So if I now imagine that I used the distance to if I now imagine that I use the distance, then you can see that I can plot a sine curve over each one of these points, which means that for each one of the points I can calculate how far away that point is in that curve. So here it would be this one, this one, this one. I'm going to draw that in red. I'm going to do it in blue. Yes, I'm going to keep it in blue. And then here, and then here, and then here, and then here, here, and here. And if I do that, then I can move. If I use those distances, I can move one more to the right, another one a little to the left, a little to the left, more to the right, nothing, more to the right, little to the left, little to the left, etc., etc. And then after that, if I add time to that, what I will end up doing is offsetting the curve by a little bit. So that it stands. Oh my god, this is going to be a nightmare to explain. Okay, let's give it a try. Okay, bear with me with this one, because I did a really bad job at drawing this on the screen, but bear with me. So remember that we had the sine function, and the sine function based on time made all the points move a little bit to the left or a little bit to the right, okay? Now they all moved the same left to the right because time was the same for all of them, and therefore the sine of time was also the same for all of them. In this case, because we want all of them to move slightly different in this kind of wave ripple effect, what we need to do is we need to find a way to use the sine function, but in a way that each one of the points has a slightly different value for the sine of something. So what we can do is we can say, well, instead of thinking of the sine of time, what we can do is we can find a value that is slightly different for all of them, but in an incremental way. So if we think, for example, of a virtual wind point that is blowing from somewhere, and if we draw a line or a vector along all of the grass curves, then it turns out that we can find the distance from each one of those points to the original wind, to the center of the wind. And because that distance is going to be increasing, if we imagine plotting the value of the sine of that distance, we're imagining this. We're not going to actually do it, but you can imagine how for the value of the wind, for each value of the distance, the sine of the distance is going to be a value that is going to grow between 0 and 1, depending on how far away the points are. You see? And therefore, What that means is that for each point, when I calculate the sign of how far away that point is from the wind, then what I'm going to get is that each one of those points has a sign that is going to oscillate between -1 and 1. And then I can use that to move that point to the left or to the right, a value that is a factor of that -1 and +1. Okay? So let me show you that in the works. So what I'm going to do is I'm going to create a point that is going to be, for example, it's going to be here. Can you see? Yes. So it's going to be here. And I'm going to bring that point into Grasshopper. I'm going to create that point. And then what I'm going to do is I'm going to create a vector between 2 points. The first one is going to be the wind. And the second one is going to be each one of the tips of the grass. Not these ones. These are the ones that are amplified. It's going to be all of this. And for the sake of visualization, I'm going to use a display component that is going to be anchored on the wind point, and it's going to be using all these vectors. You can see that all these points are going to be, and you can see that time is something, you see, exactly. So you can see that these vectors are pointing to each one of the tips of the grass before the wind is sweeping. Now what I can do is I can take the length of that, vector. I can calculate the length. Actually, the length is already calculated here, so I don't even need to calculate that myself. So I can take that length, and I can use that length to calculate the sign of each one of those values. And then as I do that, you can see that now when I move my points, the points get moved in a way that it's that some of them go back and some of them go forward. Okay, this is going to be difficult to see. You can see, for example, can you see if I move the surface a little bit? Can you see how some points move more than others? Can that be appreciated? It's very difficult to see, right? What if I crank up the amount of grass threads? What if I make this 1,000? Are we going to see that effect? I think we kind of see that effect. Can you see how there's like very 5 distinct groupings? This one, this one, this one. Can you see how there is a sort of distribution? There is like some more clusters here. And if I move this, you can see, if I move the surface, you can see how they recluster again. Okay, so this is starting to look good, but I think it's going to look even better when I do the following operation, which is going to be, because now this is static. And the idea is that I want to mimic the wind blowing through this grass. So each one of the grass threads has been moved by an amount that is equal to the distance. But if I want to make that dynamic, what I can do is, to the value of the distance, I can increase that artificially by another value that I'm going to call the time. And what time is going to do is that for every value of the distance, what I'm going to do is I'm going to be adding time to that value. What that is going to result is in the imaginary sine wave that I have on top of this. That imaginary wave is going to be displacing because I am increasing the value of distance by another value of time. So you can see how that would move to the right, and therefore each one of the points now is going to have an increasing or decreasing value of the offset for the tip. So that is just going to be as easy as taking the length that I calculated and to the length adding the value of time. And as I do this and I plug this into the sine computation, are you ready for this? It's going to be very cool. So what I can do now is I can, wait, let me zoom in here because it's very cool. Can you see the ripple effect? Can you see how there are this like wavy effect going on? Choo, 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 choo. How cool is that, huh? Alrighty. I think this is kind of, and what if the wind was coming from this direction? Wait, so that wind is going to come from the corner. So now you can see how the ripples are going to have like, are going to become, you see, can you see how they're actually kind of, because they're forming like circles because can you see those circles? Choo choo. And actually, something that I don't like is that they're moving in the X direction. They're not respecting the direction of they're not respecting the direction of the wind. So now, and that was because I had hard coded here an unit Y vector. So what I would like to do is I would like to take the direction of the wind, which is this vector here, and I would like to make sure that the amplitude, I would like to create new vectors that are the same, but they have this amplitude here, the amplitude of the sign, and use those for moving. And then, as I do that, now you can see that now that the wind is actually is blowing in the direction of where it's coming from. So like this one here, can you see now what? And if we look this way, you can see, can you choose a different visualization? No, this one is a little busy. Well, I can do that, why not? So I'm going to start, right? Whoa! How cool is this? Huh? All right. Well, I think that's where I wanted to get to with this exercise. Was this cool? Did you like this? Um, I think it's pretty cool, actually. I think it's pretty cool. Now, I probably want to talk about animating sliders. This is a really useful technique for animations. So, animate, perspective, include a frame count. I'm going to do 200 frame count. I'm going to browse. I'm going to create a new folder here on the desktop, and it's going to be animation. And then I'm going to do this. And I'm going to use BMP. Yes. Ooh, my computer is blowing up. Ooh. Let me see if this works. Yes. Should I do a video just on that? Maybe I should do a video just on that. I'm actually going to do a video just on that. That's a good idea, actually. Yes, I think that's where I want to leave this video, but I actually had a great idea because we have created a grasshopper definition that can kind of, by the variation of one parameter, show us a nice smooth animation. What I would like to do now is I would like to show you how to actually automate the generation of a series of screenshots that represent this animation, and therefore you can create frames for a GIF or for a video representing that animation. So, but I think I'm going to actually record a new video out of that, okay? And so I will, on the next video, I will explain how to take what we have right here and animate this slider to create a sequence of frames and turn those into an animation. So follow me out on that video. In the meantime, thank you very much. And maybe like this video, maybe follow the channel, maybe turn on notifications, all those things. All right, let's go to the next video and let's animate this thing and make a nice, cool video. All right, see you. Bye. And then I'm going to talk about what we are doing. So this is going to be the intro video. Hello, this is Jose Luis here, and welcome to another hands-on exercise on the series Introduction to Parametric Modeling. For this exercise, we're going to practice a little bit of randomness as well, and also, in a way, we're also going to do a little bit of practicing of very controlled, very fine-grained randomness. Because what we're going to do is we're going to model a grass patch. We're going to model a patch of soil, of turf, whatever, that has grass sticking out of it. So what I would like to show you is how to take, for example, a surface and model these curves that look a little bit like grass that is growing tangent to the surface, but it ends up going in the pure vertical direction towards the sky. And I would like to show you a little bit how to add a little bit of randomness so that the tips of each one of these grass threads are not on the same level. It doesn't look like the grass was just mown, but it looks a little bit more uneven and give it a higher sense of naturality, if you will. But what I would like to show you as well is we're going to do this exercise in two parts. The first part is going to be the random distribution of the grass threads and the random heights, which is going to be super easy. And then the second part of the video is going to be showing you how to crank this up and how to do this kind of effect where the wind is going to be blowing through the grass, and it's going to create a super interesting effect of if we have a variable that is called time, about how the wind actually blows over this patch of grass with this kind of ripple wave effect, which I think is going to be pretty cool. Okay, and by the end of the video, or maybe on the next video, I will show you how to actually take this and animate this slider to create an animation that you can publish on your website, or that you can share with your clients, you can send to a competition, whatever you want to do with that animation. All right, wonderful. Without further ado, let's get started. All right. All right, so that is going to be this wind-swept grass. Now the next video is going to be what? Oops, no, what have I done? Don't go. Here, exactly. I'm going to turn this off and turn this off. And I'm going to this one here. Okay. I'm going to take the points here also. These are going to be the outputs. Oh. Okay. So so for example, let's say I edit this, make it 10, 20, 30, for example, which is roughly, yeah, edit the value of 30. Yeah, 30 is roughly, it's about okay. Hello, this is Jose Luis here, and in this video I would like to teach you how to animate a grasshopper slider so that you can generate frames for an animation and then take that animation and generate like a GIF or generate a video, etc., etc. The way that's going to work is I have this grasshopper definition that I made in my previous video on this series, which is a wind-swept patch of grass. So what we have is a surface with a lot of curves that are growing out of them and that representing, for example, grass. And what I have is this one slide that they represent time. And as time goes by, you can see that we create an animation effect where the wind is blowing over the grass with this very interesting ripple effect. Imagine like a field of wheat with a very strong wind blowing over it. And what I want to do is I want to take this that I'm seeing right here on my screen, and I want to actually create an animation that I can share with colleagues, that I can post on social media, whatever that is. So Grasshopper actually has a way of creating this kind of animations automatically, which is the following way. So if I right click on a slider, you can see that there is an animate option. And if I click on the animate option, you can see that there's a bunch of things that I can choose. For example, I can choose where in my computer the frames are going to go, and I'm going to choose a folder called animation on my desktop. And what this is going to do is it's going to take screenshots of this screen, especially if I click on this button, so that I adapt the size and the resolution of my screenshots to my current viewport here. So if you want a different viewport, you can maximize this. For example, if I want something like this, I can maximize my viewport, and now I can right click here, animate, and when I click here, you can see that the size of the resolution is now the same as the one I have in my viewport. And then what I can do is I can choose how many frames do I want. What Grasshopper will do is it will divide the full range of the slider in values that match how many frames do you want, and therefore it will automatically advance over this slider at those increments. So for example, if I say here, I want 500, I want an animation that is going to be, for example, 10 seconds. And if the animation is 30 frames per second, I want, for example, 300 frames. Or let's do a 20-second animation. So that's going to be 600 frames. What I can do is I can now hit OK. And then what you can see is that Grasshopper is increasing this slider at tiny intervals, matching that frame rate that you specified. So you can see that it's now generating frames over and over, and it's actually taking a little bit of time. So it's taking about like 55 seconds left. So I'm just going to pause this and then I'm going to turn back on when it's done. Okay, so it looks like it's about to finish. It's only like a couple seconds left, and boom, it's done, right? So now if I go to my desktop, you can see that on my desktop I have a folder called animation that has a bunch of BMP files being those screenshots. And if I double click on the screenshot, you can see that the image that I get is this one, which is basically a screenshot of my viewport. And if I start scrolling through my image one at a time, you can see that I can take each one of them is one of the frames representing that motion for the animation of the slider. So I have 600 of these frames. So now with each one of these frames, I could take them to a video editing software like Adobe Premiere or After Effects or something like that. Or there are actually also a lot of online services out on the internet that you can just upload a bunch of images and they will generate an animation for you. So with this, now you can generate an animation however you want. I'm going to show you a really quick way of doing this with a command line tool, even though I'm not going to get into the details, but let me show you how I would do that, for example. And let me try it first before I do. So that would be FFmpeg. So that's be frame and then d.bmp and then animation.mp4. Data found. What did I write? Frame. Maybe the D is not there. Well, let me look. I always mess this up. So I have the cheat sheet here that I use. Huh. That's that's what I just did, wasn't it? Okay, so let me see. Yes, I have all of this here. FFmpeg. Video from frame. So frame rate 30. Input is going to be frame underscore d dot. It's 5 digits, right? Yes. Dot bmp and animation dot mp4. What the hell? Why is this not working? Do I have to turn? Excuse me. Why is this not working? Is it not taking BMPs? Is this what's happening? Do I have to? Is there a way to output PNGs from here? PNGs. Oh God. Let me do this again. Animation PNG. Yep, it doesn't take BMPs. Interesting. Yes, I can output PNGs. But they're not real PNGs, they're still BMPs, which kind of sucks. Uh-oh. Did I mess up by scrolling? Yes. Oh no. Ah. Oh no. No. So I have I scrolled while this was going on. Oh my God. Okay. So yeah, so that's, let me do this again. Is it possible to animate sections using clipping planes in Grasshopper? I think I've done that in the past. I forget how I did that, honestly. But I think I've done it. How did I do that? I'm not sure, but I think I've done it. But I'm not sure now anymore. No! Oh, God. Okay, we're almost there. All right, and then I have the animation here. I'm going to do this. I'm going to create the animation. And then this is the animation. Woohoo! That's pretty nice. Okie dokie. So I'm going to show that. So as I was practicing doing this, I actually realized that the tool that I use does not take BMP extensions for files. So what I ended up doing was I ended up exporting this again, but instead of doing BMP here, I used PNG, which is a different file format, even though at the end of the day, it ends up, when Grasshopper exports, it still ends up being BMP for real. It doesn't really use PNG. Anyway, but long story short, I had to do that hack on my own, but maybe you don't have to do that by yourself. But anyway, I had to render this again, and I ended up with a folder called animation PNG, which has the same files, but in PNG format. What I like using a lot for this kind of generation of animations is a tool that is called FFmpg. So FFmpg, which is a command line tool for converting, re-encoding videos, etc. It's a really, really useful one. And it's a very, once you install it in your system, you can open a terminal on the folder, right? So I'm right now on the folder that I'm using, that I have all these animations, and I can say, I can call FFmpg and say, for example, that I want to create a video at a frame rate of 30 frames per second. I want the input frames to be a series of files that are called frame underscore, and then I can use this special notation to say that after that there are 5 decimal digits that are correlative. So I use this like percentage sign, 0, 5, and D to indicate that there's a sequence of 5 digits. Then I type the extension of the file, and now the name of the outcome, which is going to be animation.mp4. And what this command line will do will be automatically go through all the frames and compose a video with all those frames in MP4 format with some default parameters. So you can customize the bit rate, etc., etc. But you can see that I have now this file here, and if I double click, you can see that I have an animation that is all the frames stitched together and very nicely. So you can see how smooth this animation is. And you saw that flickering. That's because while I was rendering, I turned off the visualization. So that's why the thing is, like, when you do this screen shooting, Grasshopper will screenshot exactly what you have on the screen. So if you want to make a nicer screenshot, you can just turn off this grid, you can turn off the visualization of this point, you can hide the surface, and maybe you want to give it some style. Maybe you want to render a one of these ambient occlusion kind of aesthetics. It's up to you. But whatever it looks like on Rhino, that's what it will look like on the screenshot. So I'm not going to get into FFmpeg as a tool because that's going to be its own playlist at some point because it's very useful and cool. But if you want to learn more or if you want to have like a quick cheat sheet, I actually have on my GitHub repo. If you go to FFmpeg, I have a full list of commands that you can use to create videos from files, extract frames from a video, create a GIF from a video, speeding up video, compression, change the size, a lot of stuff. So you can look for my GitHub repo FFmpeg cheat sheet. Okay, if you want to learn more about that. Otherwise, this is creating animations. And otherwise, if you don't want to use FFmpeg, just take all those frames and use some video editing software to stitch them together and render a video. That's also absolutely fine. Okay. All right, so this was creating animations from sliders. Thank you very much. Maybe if you like this video, just maybe like it, maybe not, whatever. Otherwise, see you on the next video on this series. Bye bye. Thank you. Okay. Were you familiar with creating animations in Grasshopper? Had you ever done that before? Um, hey, Salvador. Hey, how you doing, sir? Okie dokie. So, all right. So, what is next? What is next? What do we have next? A facade with random rectangular panels in two directions. Ooh, that's going to be fun. Okay, so let me get some stuff here. I'm going to save this. I'm going to save this, and I'm going to create a new file and a new file here. No template. Okay. And I'm also going to go and drink some water because I'm a little dry. I'll be right back. Hold on. Okay. What are we going to do? We're going to do a facade. Um, Random panel facade. Let's see if I have any. This could work. Something like this could be. Mm-hmm. Uh, yeah, can you hear me? Is the audio? Yes, the audio is good. Yeah, grasshopper, of course. Mm, okay, I think what I want to show is closer to this idea. Copy image, save image in a new tab. Mm-hmm. So how are we going to do this? Well, let me save this stuff here. And then let me create a new sketch. Mm-hmm. Okay, I think this should be easy to do. So let's start with the basics. So I'm going to start here and I'm going to say, what I have is a facade. Oops, I have a facade. Okay. And what I want to do is I want to divide that facade in something that looks like this. Something that looks like, for example, random division, random division, random division, and another random division, for example. And each one of that in turn is going to be have like random panels like that. It's also going to have like random panels like that, for example, and random panels like that. Like that, and then random panels like this, for example. So we want to create something like that. And what are our parameters going to be? Well, we probably want to control the height, and we probably want to control the width of the facade. That's one thing, right? And maybe for the sake of having some kind of extra control, we're also going to control maybe for each the number of elements in the height direction, and also we're going to control the number of elements in the width direction. So those are going to be parameters that we're going to control. And then for each one of those, so then the process that we're going to follow is going to be something like this. We're going to create, how am I going to explain this? What I want to say is that we're going to create 5 random numbers. How am I going to say this? I'm going to say that we have 5 random numbers. Like in this case, right? So for example, I have I'm going to say I have 5 random numbers, and those are going to be 5, 3, that's going to be 2, 7, 6, 4, and 8, right? And it turns out that if I use those numbers right away to create, they may just not match the height of the, because they might create panels that would be something like this. They would be something like 8, for example. They would be like, how can I do that? It could be 8, 4, 6, 7, and 2. It could be 8, 4, 6, 7, and 2. And then, because they're just random. But what's important is that with that, I could potentially calculate how much their total is, which in this case is going to be 27, right? But if I know their total, and if I know h, then I can multiply. But if I know their total and I know h, what I can do is I can multiply each one of these numbers by how much larger it has to be, and that's going to be h divided by 27, and it will give me a set of values that will match exactly the height of the whole thing. Height divided by 27. It will give me that height. And then we will address in that dimension, we will address it at a later stage. Okay. All right. So I think that's how we're going to start. And actually, I don't really need to do this. If I'm going to show the thing working anyway, I don't even. If I'm going to do an introduction where I'm going to show that image anyway, I don't need to. Okay, so I can just start right away with this. All right, let's do this. And I may want to stop. I may want to stop just before I start explaining the problem so that we can see the problem actually happening. Mm-hmm. Yeah. Yeah. Okay, as usual, let's do a little bit of sketching to use our brains to think through the problem, and then we can, before we go into actually developing anything. So what we want to create for example, the facade of a building, and what we want is in this facade, we want to create it with some kind of pattern that feels random. So what we want to do is we want to probably have, for example, rows of panels, and each one of those rows is going to have a height that is going to be random. And then within each one of the rows, we would also like to subdivide that into panels in a way that the dimensions of each panel is also in a way random. This could be nice for designing a facade. This could be nice for designing like the layout of some stones for a facade. It could have a lot of applications, right? Now, the problem here is going to be how do we tame the randomness so that it actually fits the constraints that we have for the facade? Because typically when we have a facade, we have a set amount of parameters. So we know that the facade is a particular height and a particular width, and we have to adapt our randomness to that. And maybe we can also get to choose other parameters, such as, for example, how many of these rows are in the height direction and how many of these panels are on the width direction. So those might be parameters that we're going to use in our definition to control the layout of the random panels. And then the process will probably be something along the lines of first dividing the surface, first dividing the facade into the rows, and then subdividing each one of the rows into each one of the panels. The way we can do that is, for example, we can say if we know that we have 5 rows, then maybe what I can do is I can just generate a sequence of 5 random numbers and then use those random numbers to drive the size of each one of the rows. The numbers that I just explained here are integers for no particular reason. They could be floats, they could be anything, right? So we're not going to be bound for that. And so let's build this up and let's start with that problem there. And then we're going to see if we run into any problems, and then we're going to go back to the whiteboard to refine this problem, okay? Let's start building this inside of Grasshopper. Okay, so bifocals, and then we're going to do, this is going to be the width, going to be the width, and that's going to be the height, for example, and we're going to draw, we're going to have an XY plane, that's going to be the base, for example, and then we're going to draw a rectangle on that plane that is going to be this width and this height, and we're going to just have that something like that. Okay, and I'm going to actually use the top view just because it's going to be easier. Okay, and then we're going to say that the number of elements in the height direction and the number of elements in the width direction, and that's going to be, for example, 5, and here might be, I don't know, 15, who knows. We'll see about that. Okay, so what am I going to do next? So I'm just going to place this here for visualization, but we actually don't care about that at all. So then the next thing we're going to do is I'm going to generate the 5 random numbers. Okay. Let me save this e.23 random panel facade, and then here we can probably also Then after this, I'm going to generate 5 random numbers. And then I'm going to create planes to generate those random numbers. And I'm going to try to create rectangles like that. Okay, so that's what I'm going to do. Let's do this. I have taken the freedom of kickstarting the exercise by dropping in a few sliders for example, the height and the width of the facade. I'm going to be, for the sake of simplicity, I'm just going to assume that the facade is on the ground, or so it's on the XY plane, just to make things a little easier. But it could be vertical. There's nothing really that prevents us from that. And then I've also dropped some integer sliders so that we can control the amount of elements in the height direction and in the width direction. And then just for the sake of visualization, I don't think I'm actually going to need this for anything, but for the sake of visualization, I have placed a rectangle defining the boundary of this facade. This is going to help us during development to understand how things are going. Well, the next thing that I would like to do is, I know that I have 5 rows, so what I need to do is I need to create 5 random numbers, which are going to be the widths or the heights of that random facade. So I'm going to create, for example, 5 random numbers. I'm going to start with 0 to 1, but I'm going to change that very soon. This is going to be 5 numbers, and then the seed is probably going to be, I don't know, some slider that I'm going to call the seed. And for this one, I don't think I will need to, well, maybe I do need to control a little bit the seed. Anyway, and then with this, I have 5 numbers that are going from 0 to 1. And then maybe if I want to perhaps like crank those up, I can just say, well, let me create a slider here and turn these random values from 0 to 10. Okay, and then I get these values here. And then what I would like to do now is I would like to move this plane here a bunch of positions so that I can draw rectangles on each one of those positions. So I'm going to draw rectangles representing the full rows. So for example, what I'm going to do is I'm going to first add a 0 to the list, because remember that I want to always have the same plane. Well, sorry. Now I'm just going to move all these planes here. I'm going to move them in the y direction an amount that is equal to those random numbers. And you can see that I got a list of planes now with all these coordinates. And just because I want to use the first plane as also a row, what I'm going to do is I'm going to merge into this list the original plane. So I'm going to merge to this list that I just created, the original plane, and then I'm going to have the exact same list, but with the first plane on it. And I'm going to, because they have different structures, you see how I'm getting problems here, I'm just going to flatten this so that I get all the planes on the same list. Okay, so now I have a set of planes here, and what I could do is I could use these planes to draw boundary rectangles representing the full row. This is just for us for visualization, okay? So how do I do that? Well, I can use these planes to generate rectangles, okay? And what is the x of the rectangle going to be? It's going to be the width of the facade. So I'm just going to place this in here. And then what is the height of the plane going to be? It's going to be each one of those random numbers, okay? So I get that there. And then you can see that I have now 5 rectangles, but you can see that the last one is duplicated. That is because we have added this extra plane that was the beginning. The beginning, we added this extra plane there. So what we need to do is we need to remove that plane, and I'm going to shift the list here, and I'm going to make sure that this is set to false, and that the list is being shifted in the opposite direction. So -1. Okay, And therefore now I have the same list, but without the last element. So now you can see how I have, for each one of the planes, I have one rectangle marking the full row. And if I do a planar surface, a boundary surface, you can see that this is going to be a little easier to see. Okay? And I think I'm having some overlap issues here. I may need to take a look at that in a second. Let me actually take a look at that right now. What have I done here? Something is wrong. Okay, so these are the heights. So 0 0.1, 2 point something, 7 point something. And those should be the so unwrap this. How is the last element? Oh, because I need to, oh, I forgot, because I need to add them incrementally. Ah, yeah. Oh, God. Okay, so maybe I should just start over here. Or not. I can just... Yeah, I'm just going to... Or should I just redo this again? I could redo this again, but I forget what I started with this. What did I start with this? Okay, well, I'm just going to... Yeah. Sorry, my bad. I was trying to record this video quickly, and of course that never works. So I forgot that these numbers are the incremental heights of each one of the rows, but those are not the values that I should use for the unit y direction. Because if I do that, then I'm basically copying the base plane, 1 unit, and then 2 units, and then 3 units, but I should copy them at incremental heights. So that is going to be achieved by using the mass addition, which is going to give me the the added coordinates of each one of these planes in the y direction. So if I do that, you can see how now each plane stacks on top of each other perfectly, and now things are working well. I actually covered this technique in a previous exercise. I forget which one was that. It was like exercise number... It was the exercise where I was doing the sections of a building and chopping them and laying them flat. So that's where I covered this technique. So you can see that now I have a collection of planes. Each one of these planes is at a height that has been moved by those incremental random numbers, so the heights of each one of the rows. And then I use those to move them and to create rectangular rows that represent rectangles that represent the rows. Okay? All right. Sorry for that confusion. That was my bad. Now, what we have here is that we have a tiny problem. We have two problems first. One problem is that we have decided that the random factor should be somewhere between 0 and 10. Because this is pure randomness, the problem here is that this may randomly give us very large numbers, which is fine, because if we set this to a maximum, that's fine. But it may also give us very small numbers. So you can see how, for example, in this case, we were very unlucky, and then we got a number that was 0.01. So very, very close to 0. And in the real world, we probably don't want to fabricate like a panel that is like a tiny, tiny sliver. So we probably want to have a large minimum so that we ensure that there is at least like a body, a corpulent body of material to make these elements with. So I would argue that perhaps we need to say, for example, here we need to move all of this. Let me create some room here for us. Let me move all of this here. And then let's say that if the range is 100, then maybe the minimum range should be a number that is bigger. So for example, let's construct a domain now that is going to go from 5, let's say it starts at 5 and it ends at 10. And that's the domain that we're going to use for the random. Okay? So this way, we are ensured that no panel is going to be like a tiny thing. All right? Now, the other problem that we're running into is that the actual facade is this big. The actual facade is this. But because we are just generating 5 random numbers, there is a very, very strong likelihood that the addition of these 5 random numbers is not going to add up exactly to the size of the facade. So you can see that that can be whatever. And if I actually crank this down, for example, you can see that now the total is like very, very much smaller. No matter how much I play with these two numbers, how much I make them closer or not closer. You could argue like, oh, well, maybe if you play with these numbers, whatever, then I can adjust this to make it almost exactly. But you know me already, that is not a clean parametric approach. So what I would like to do is I would like to find a way to find a rule to take all these numbers and make sure that they add up to the height of the facade. And actually, that is going to be a super, super simple rule. If you think about it numerically, you can say, well, we have the problem that we've generated 5 random numbers. And when we use those random numbers to generate rows, it turns out that those numbers end up being like smaller than the facade. But it turns out that I can actually very easily modify those numbers, because if I know that the total of those numbers is, for example, 27, but I also know how high the facade should be, which is h, for example, let's say it's 50, then I know that those numbers should be roughly double in order to fit the facade entirely and exactly. And I can actually find what the proportion of these numbers should be by saying that those numbers should be amplified by a factor that is equal to the total height of the facade divided by the total height of these random elements that I just got here. Okay? So this whole thing here is the amplification factor that if I multiply each one of the numbers will give me a set of new values that are 1.7, 1.8 times bigger, but it is guaranteed that their sum, all of them together, is going to add up to the height of the facade. Let me show you how that works. That's a very simple numerical rule. So for example, here in mass addition, we know that the second parameter, partial results, give us the incremental additions. But we also have the result, which is the total height. So if we take this result, which is the total addition of all the numbers, and we divide division, and if we divide the total height of the facade, which is this one, we divide the total height of this facade by the result. Then we're going to get here 1.74, which is the amplification factor. And if we now multiply, if we now multiply that factor 4 by all the random numbers, we're going to get a new list of random numbers that is slightly bigger, but it maintains the proportion. And if I now do mass addition on that one, and I add all the partial results, and I add them all together, you can see that I'm now getting all these rectangles, which are, sorry, I need to plug in this partial, I need to plug in the new sizes, not these ones, but these ones. Yes. So you can see that now I have all these rectangles that are perfectly matching the size of the and now if I modify this, the only thing that I'm modifying is the relative size. I'm actually not modifying the absolute distance. So the actual numbers here, they don't really care. What matters is the actual relation between them, which I think is a really beautiful thing, actually. So, all right. So I think with this, we solved the problem of the rows first. Now it's only a matter of solving the problem of the individual columns for each one of the rows. Okay, so I'm going to group this. This is going to be inputs, and this is going to be vertical variation, and this is going to be random numbers, blah blah blah, here multiplication, mass addition, whatever, and then that's going to be the planes. That's going to be one thing, and then here is going to be, oops, that's going to be, what am I doing here? Okay. Now, the problem that we're trying to solve here is going to be the exact same one that we did for vertical. It's just in a horizontal way. And it's going to be for each row, I'm going to need to generate a sequence of random numbers that are going to be whatever. And then I will need to figure out their mass addition, their factor of expansion, and then extend them to cover the whole row of the facade. And that is going to be the same for this one, it's going to be the same for this one, and it's going to be the same for this one and for each one of the rows. But because I'm not going to do this manually, I want to do this automatically for each one of the rows, I will need to create different random sequences for each one of the rows and make sure that those sequences are different using different seed numbers. So it's going to take up a little bit more of data manipulation than before. So so bear with me and let's try to see how this works. Okay, let's go back to Grasshopper. The first thing that I need to do is I'm going to start using numbers, just like straight numbers, because it's easier to explain things. We have right now 5 rows. So what I need to do is I need to create 5 lists of random numbers, each one of them containing 15 random numbers, which is the number of panels in the y direction. So I need 5 lists of 15 random numbers. So how can I do that? Well, should I place the random component and then just copy paste it like 1, 2, 3, 4, 5, 6, 5 times? Is that what I'm going to do? I hope at this point no one is thinking that that's what we're going to do, because that is a really terrible parametric approach, because that basically hard coding the problem, and if I increase this by more or less whatever, I would need to rewrite this part. So that's obviously not a good approach, okay? So you have never thought about that. So I'm going to take, that's not what we're going to do. We're going to take one random component and we're going to say, I need to generate lists of 15 values, okay? And as you can see, I actually reorganized a little bit the definition. And what is going to be the domain? We're going to do something very similar. We're going to say that we're going to create another group. We're going to create another domain here. And that's going to be the horizontal variation. So horizontal variation is going to be 2 sliders, the minimum and the maximum, and that's what I'm going to plug in here, okay? And the seed is going to be, for example, is going to be, I don't know, 1,000, okay? If I do that, then the result that I'm going to get is that I'm going to get one list with 15 numbers, okay? Very clean. But this is not what I need. What I need is 5 lists of 15 different numbers. So why am I only getting one list? Because here, as an input, I'm only inputting one domain, I'm only inputting one number of random values, and one seed. So obviously, the result of this is going to be just one list. Now, what I will need to do is one of these inputs is going to have to be a list of data, right? So for example, let's say that, so that when we create this, we get different branches of data. So for example, what I could do is I could create a panel and then hard code, for example, that this panel is going to contain the number 0, and the number 1, 2, 3, and 4, for example, because I have 5, I want to create 5 lists. And I'm going to say that this is going to be multi-line data. And I'm going to plug this here as the seeds. And because I have different seeds, you can see that I now have, for each one of the branches, I have a different list of random numbers, each one of them with a particular distribution of these numbers. However, obviously, this is not parametric, because if I now have like more than 5 rows, this is still 5 numbers, etc., and it's not cool, okay? So we're not doing that. We're going to be a bit more elegant, and what I'm going to say is, instead of doing this, I'm going to create a series of numbers. And the first one could be 0, but so that I have connection with the variability of this, what I can do is I can say the first number is going to be whatever my seed is, which I've already used for the horizontal distribution, whatever my seed is plus 1, because I don't want to use the same seed for 2 random distributions in my panel. So the first one is going to be the value of 1001. Then how many numbers do I need in this series? I need 5 because I need 5 different seeds. No, sorry. This is n is the step size, right? Yeah, so the step size 1 is fine. And then I need 5 different numbers. What this gives me is 5 different seeds from 1001 to 1005. And if I ever change the seed, I will get like a different set of seeds, right? So what I'm going to do that is I'm going to use those as the seeds to my random list generation. And now you can see that my panel has branches, it has 1, 2, 3, 4, and 5 lists, and each one of them containing a different set of random numbers. Okay? Wonderful. So now the only thing that I need to do is I need to follow a very similar process to this one, where I'm going to find the mass additions for each one of these. So I'm basically copying what's going on here. I'm going to find the mass additions, and I'm going to see what those look like. These are the numbers that I'm getting, but these are the partial results. Okay? So the partial results, I'm going to move them. I'm going to use them as x vectors, and then I'm going to move each one of the planes that I got here. I'm going to move each one of those planes. I'm going to move them by each one of these vectors. And as you can see, I am getting data problems because since I have here a list of 5 elements, the first 5 elements of each one goes with the first 5 elements of each one of these. So you see, that is why I don't like flattening things directly from the output. So I'm actually going to do exactly what I always tell everyone not to do, which is what I always tell everyone to do, which is use flattening components, because now I actually don't want this flattened. Okay, correct? So what I want is I want this data to be grafted. So I want this to be grafted, and I want this graphed here to give me now different planes, you see, for each one of the rows. So now I have 15 planes for the first row, 15 planes for the second row, etc., etc. And you can see that if I change, I just happen to have a distribution that was very close to the size of the thing. So if I now plot rectangles here, on these planes with an x that is going to be equal to, to the planes, I need to merge the original planes here. So I'm going to need to merge this so that the first plane is plane number 0. Okay? And you saw how the first one was not included. So I need to add the first ones. I need to merge them so that the first one is also included on the list. And now I have 16 rectangles, and I need to shift the list so that the last one is not repeated. So I need to shift that one. I need to shift the list so that the last one is not included. And what I want to do now is, and I'm not doing this correctly because I'm not adding the first one. Yes, so I need to add here to these planes, I need to add, okay, well, I will fix that in a second, okay? But then I'm going to take the x sizes, so those are going to be the ones that I have here, and then the axis are going to be the values that I have here. So those are going to be these ones here. Oh no, and it's not working. What is going on? Well, it looks like I have data problems. So let me try grafting this. So I'm going to unhook this from here and hooking it here. And now it looks good because this should be here and this should be here and this longer one should be here and this one should be here. So I have a problem with data. So what I need to do is I need to add to my original list of planes, I need to add the number 0. So actually, I can probably just add that here. So I'm going to add the number 0, and I'm going to merge this with each one of the branches, and I'm going to plug that in here. And it's not working. Okay, because it's not the same data structure. Yes. Okay, so let me think about this and do it in the right way. Hold on, give me a second. All right. So what is going on here? Okay, so what is going on? So it looks like I have 5 elements that have been moved in the y direction. And so I need to flatten this, I need to merge this, and I need to take this. And this is what I should graft in here. Correct? Yes. All right, use your brain. So now I don't know where I was before I did all this mess. Okay, I found it. The problem was that I was bringing in the collection of planes that didn't have the first one, and those were the ones that I was grafting and bringing into my series. And it turns out that what I actually need to do is I need to bring in all the planes that have just the first ones and not the last one. So those were here after the merging and the shifting. So if I plug that in here, and if I graft, you can see that now all these planes have the right sizes, and they're all matching the row at which they are in. Okay, so yes, whenever you have complicated data problems, don't rush into it, because you're always going to mess up. I do it all the time as well. So now that I have this, you can see how I have a distribution of panels in the row, but obviously these panels are not fitting the dimension of the row, because what I need to do is for each one, I need to do the same process that I did before. For each one of the random distributions of numbers, what I need to do is I need to calculate the total of that row. And what I need to do is I need to, as per the rule that we discussed before, what I need to do is I need to calculate what is the distance of the total row divided by the total distance of panels that we have right now. And that becomes the factor that I need to use to multiply, to amplify this by. So what I'm going to do is I'm going to divide division, I'm going to divide the width of the facade by each one of these total results, and it's going to give me the amplification factor. So now I'm going to multiply each one of these numbers by each one of these amplification factors. And you're going to see that if I had this original list, what I'm going to have now is a tree that has the numbers multiplied by 1 point something. So it's not too much. And then I'm going to calculate the mass addition of each one of these. And I'm going to use the partial results for the translation vector in the x direction. And I'm also going to use those new sizes as the x width of each one of the panels. And as you can see here, now I have the facade that has been subdivided in random panels in each one of the two directions. I'm going to disable all these planes and all this. I'm just going to turn everything off basically. And I'm going to stay with this. Okay. And then I'm going to add here rectangles, and I'm going to bring this to the beginning of my definition. Wow, this ended up being quite some spaghetti, huh? Ugh. Okay, so I'm going to leave it up to you, the viewer, to make a better case about ordering these things and making it look clean. Okay, so I'm going to hide this, and this is going to be the output. And then you can see that now, very nicely, we have the rectangles here. We can do planar surfaces if we want. Boundary surface for each one of these. And we can very parametrically amplify the facade in one direction, amplify the facade in the other direction, more elements in one, less elements, more elements. This looks pretty nice, like a stone wall of sorts, right? Less elements, or for example, we can have more elements in this direction, less elements, and if we change the seed, we just get absolutely different random distributions. Similarly, we can play with the vertical variation. If these two numbers are very close together, there's going to be barely any variation, but if they're very far apart, we get a lot of variation. And similarly, here, if there is no variation, look how they almost look like a grid, whereas if we crank up the variation, then there's much more difference between them. Now, I would like to conclude this exercise by reflecting on the fact that what we've done here is an exercise of pure mass customization, because the size of each one of the elements is absolutely random within this control variability that we have generated, but they are random. And each one of the panels in this facade will have a different width and a different height. This typically is very expensive to build, for example, because if we have random panels to choose from, typically we have a particular set of measures that we can choose. Maybe we have like 100 centimeters, 150, 200, 250, and 300. And those are the only panels that we can choose. We cannot choose to have a panel with like 267.5 width, you know? And cutting them would be super expensive. So if we wanted to generate a version of this, where instead of having absolute freedom to choose the dimensions of each element, we wanted to constrain it to a set category of different options, then the technique would be similar, but with a few changes, okay? So I'm not going to cover that right now, but perhaps I may cover that in a future exercise, in a future video, whatever, or in an algorithmic modeling challenging, who knows? But I think this has been a pretty good exercise about working with randomness, but in a way that we can control. So controlling variation, controlling offset, and controlling amount of elements in each direction, and controlling seed values to not be repetitive. So I think with that, I am very happy with where we are. Thank you for sticking around to this video. I hope the whole data part was not overwhelming, and I hope that you could keep up with my back and forths. I'm sorry about that. And thanks a lot. And if you learned something on this video, maybe consider liking it. Maybe you want to subscribe to the channel, and maybe you want to hit notifications to get emails or pop-ups on your phone when we go live or when we publish new videos. In the meantime, thanks a lot, and I will see you on the next videos on this series, hopefully. Bye bye. All right. Okay. So are we going to... Okay. Let's record the introduction and then we're going to take a lunch break, right? Because I'm pretty hungry. I didn't have breakfast today. So we're going to do that. How was the exercise? The data part was kind of confusing, right? I did not do a good job on this one. I'm sorry about that. I should prepare. I should prepare more the exercises, I think. Anyway, let's record the introduction. Hi, and welcome to this series where starting over. Hi, my name is Jose Luis, and welcome to this new video in the series Introduction to Parametric Modeling, where we're going to do a hands-on exercise on generating a facade that is made out of randomly sized panels. And the way it's going to work is that I have this definition. I'm going to create a definition where I have control over the size of a hypothetical facade, and I have control about how many elements are in each one of the horizontal and vertical directions. But I also have control over a certain random variation of sizes that is going to be affecting the panels in each one of the X or the Y directions, as well as having the possibility of play with the seed that is generating this randomness to generate different versions of facades with different distributions, different random angles, not angles, the different random sizes, etc., etc. So with this, now I can create more or less, and this can be an interesting exercise for creating a stone facade, for example, or for creating a facade with panels, and maybe I could even randomly turn on and off certain panels to have like windows and openings. This could be an interesting exercise. This is going to be an interesting exercise to learn how to use randomness, but in a controlled way, in a way that we can explore variation, ranges, and differences, and not just pure absolute randomness. But at the same time, it's going to be a super interesting exercise on data manipulation, because we will actually need to do fairly a few data manipulation procedures like merging streams, flattening data, grafting data. We're going to do a lot of that in this exercise. And I don't think I actually did a great job at explaining that. But if you have watched the previous videos on this series, hopefully you'll know enough to bear with me perhaps speeding a little bit or going a little faster over those topics. So less talking and more doing. Let's go to the whiteboard and let's first think through the problem and do some diagrams before we make before we write any code. Okay? See you there. All right. Oh, wow. Oh my God. Okay, I'm going to save this. I'm going to save this. Oops. Oops. Okay. And oh, oh, Salvador, you like the debugging? You must be a masochist, man. Why do you do this to yourself? No, I do. I do understand the part of seeing someone in trouble and seeing how they try to fix their problems, and that being a learning experience. But I can also see how that can be a painful thing to do. Anyway, thank you very much for being there. I'm gonna go grab lunch, and I'm going to take a quick break. And then I will be back in the afternoon, and we're going to do this afternoon is going to be really cool. We're going to do an exercise where we're going to do a brick wall, and we're going to explode it. And the bricks are going to like fly like that right away. It's going to be very, very cool. Okay, and we're going to use a lot of randomness for that. Okay, thank you very much. Hey, Dusko, I didn't know you were there. Thanks a lot. Have a good one, and see you this afternoon at 2 p.m. my time, so in 1 hour and 15 minutes. Thanks a lot, and we're almost done with the playlist. Woohoo! Woohoo! Thanks a lot. See you later. Bye.